Hello everyone, my name is Maciej, I'm a product marketing manager in IntelliJ Scala team. While I was a software Scala developer for many years, nowadays I'm mostly focused on making content on YouTube, like this video, on going to conferences and talking about Scala on conferences and on meetups. You might be thinking now, wait, but this is a video about Kotlin, not about Scala. And yes, that's right. In the best tradition of social media, especially Reddit and ex-Twitter, since I'm not a software developer anymore, and since I don't know that much about Kotlin, I'm going now to tell you my opinions on how you can write your Kotlin code better.
The thing we're going to focus on is a pretty specific concept that you're probably already familiar with. Let's look at two methods from the IntelliJ platform codebase written in Java. In the first example, you'll see a neat use of early returns which act like a filter for the data passed in the parameters. The editor reference is passed to the method and we first check if it's not null. If it's not, we move to the next line where we use it to get the offset of the caret. Then we use another early return to exit the method if that offset is 0. Now let's look at another way to achieve the same result, a sequence of consecutive checks on the data passed as parameters. This approach isn't necessarily bad, and in fact I would say there are times when it makes perfect sense to write code like this, but when we compare these two methods, it's easy to see how early returns can make your code more readable. And that's the definition of good I will be using today. Good code means readable code. However, there are situations where early returns can lead to suboptimal code. One such scenario, which I will focus on, is when we have an early return inside a loop. We process some data, iterate through it, perform operations, and then find an element that meets our criteria, which we return. If we don't find that element in the entire loop, we return null. Let's write such a method. We will call it findFirstValidElement. It will take a list of code snippets as a parameter, iterate through them in a for loop, and for each code snippet it will convert it, try to validate it, and if successful, return that valid converted PSI element. If I wrote this in Scala, my reviewer would likely tell me that this approach is totally unacceptable. In Scala, we almost never use the return keyword. In Kotlin, however, it's much more common, even in situations like this. So I'd like to draw on my Scala experience and show you a few ways to write code like this without early returns, while still keeping it performant and readable. But first I need to ask you to use your imagination. The situations where code becomes too complex and early returns become problematic usually happen in large code bases. On the other hand, I need to keep the code simple to make the video reasonably short and interesting. So, I'll rely on you to imagine that the code I show you is much more complex than what you see on the screen. We have code snippets, like this list here, and these snippets will be converted into some abstract program structure interface elements, PSI. Of course, this is all just a mockup, designed to give you an idea that we are developing an error highlighting system similar to the one in IntelliJ IDEA. Here we have PSI elements representing different pieces of code, variables, literals, and so on. We parse code snippets and try to convert them into these PSI elements. Sometimes these PSI elements will be valid and sometimes they will be invalid. We have a convert function, and please imagine that this function takes a significant amount of time to convert a code snippet to a PSI element. It's quite expensive to call. Then we have another function, validate. Let's say there's a context like a data store of other PSI elements in the entire program, and the validate function checks if this new PSI element fits with all of that. This means a code snippet might be successfully converted to a PSI element, but that PSI element could still be invalid. And just like the conversion, the validation also takes a lot of time. Now, our task is to convert and validate code snippets from a collection we receive as a parameter. If we find a valid PSI element, we want to return it immediately. Since both the convert and validate functions are costly, we want to avoid calling them more than absolutely necessary. That's why we have this early return here. You might be thinking, okay, this is very simple, and the return here is easy to read. So what's your point? Why should we change it? But remember, I asked you to imagine that this code is much more complicated. In fact, let's make it more complicated right now. Suppose the convert function might not be able to convert a code snippet, in which case it returns null. Additionally, let's say the validation is unsafe. The validate function might throw an exception, so we need to wrap it in a try-catch block. On top of that, we can have a secondary validate function. If our main validate fails, we might still consider the PSI element valid if some other requirements are met. For example, if the PSI element is a variable, we have a specialized variable validate function for variables, another one for literals, and so on. Hopefully you can now see how, as the code becomes more nested, their early returns become harder to spot. Sure, you might say, I'll just read the code carefully and find it. But the thing is, it would be even better if you didn't have to be careful at all. If that return wasn't there, you wouldn't have to look for it. You might also say, alright, we can extract some simple private methods. They will encapsulate pieces of code and make find first valid element easier to read. Great, I really like that idea, but early returns don't let us do that well. Not really. Let's say we write a method called save that encapsulates the try-catch block here. The problem is, if I replace the original try-catch with the save method, I still need to write the early return outside of it. I can't jump out from the save method to the outside of find first valid element. So I still need to write something like this, and it helps, but only a little. By the way, we can run this imperative version of the program now. It finds the first code snippet that can be converted to a valid PSI element and returns that valid PSI element. Please note that we don't return the original code snippet, but its converted form. This will be important soon. Now, let's rewrite the find first valid element method in a functional way. We'll use methods from the standard collection library, such as map and find. First, let's write a naive version where we convert all code snippets to PSI elements and then find the first one that is valid. But as I mentioned earlier, the convert method is costly. If, after converting all code snippets, the validate function finds that the first element is valid, it means we converted many code snippets unnecessarily. We can try to improve it a bit, still using a somewhat naive approach. Let's call this version less naive. For each code snippet, we'll convert it and validate it inside the list's find method. If the PSI element is valid, the find method will return the original code snippet, and then we'll convert it again. This is better than before, but we are still calling the convert function twice, which isn't ideal. Fortunately, the Kotlin collections library has methods that can help us here. First, there's the first method, which works like find, but throws an exception if it doesn't find any element that fulfills the predicate. Then we have first or null, which works exactly like find. If there's no element that fulfills the predicate, it returns null. There's also first not null of, which we can use to map the element. If the mapping is successful, first not null of returns the converted version. If not, if the mapping returns null, then first not null of throws an exception. This mapping or transformation inside first not null of is our way to check if the element is valid. Lastly, there's first not null of or null, which does the same thing but simply returns null instead of throwing an exception. I don't know about you, but first not null of or null isn't a name I can repeat many times without misspelling it. So let's quickly create an alias for it. We'll call it collectFirst. That's the name of a method that does something very similar in Scala. In the new version of findFirstValidElement, we use collectFirst and write a lambda that takes the code snippet and converts it to a PSI element. Then we validate it, and if the validation is successful, we return the PSI element from collectFirst. As you can see, all of this now becomes just one very simple expression. That's it. That's the functional version of the original imperative for loop, and it doesn't use the return keyword. But what about that more complicated version, where both convert and validate methods could fail, and where we have additional secondary ways to validate? Well, let's see. Let's write a slightly more complex version of this new functional findFirstValidElement. We have the nullable convert function, and nullability in Kotlin is easily handled with the question mark operator. Thanks to this, the rest of the logic will only execute if nullable convert returns something that is not null. Then, within that logic, we'll put the unsafe validate function and wrap it in safe. This way, if validate returns true, we'll return the PSI element immediately. If it doesn't, we still have the option to use other validation methods. For example, if I know that this PSI element is a variable, I can use smart casting here and call variable validate to determine if that variable is valid or not. When we compare the two versions, this one and the complex imperative one, we can see that they are equally performant and equally difficult to read. Let's do something about that, shall we? Kotlin 2.1 introduced when guards, allowing us to write more complex logic in when expressions. If we are okay with the code becoming a bit longer, but also more readable, we can try them out here. We can write the when expression directly inside collectFirst. We'll put the nullable convert function here to create the converted PSI element and immediately pattern match against it. In the first line, we'll check if the result of the conversion is null. If it is, the whole when expression will return null as well, and collectFirst iterates to the next element. If it's not, we move to the next line. Then we go line by line and check if the PSI element, which we know now that it is not null, so we no longer need to check for it, if it fulfills the given case. If yes, we return it. If not, we move to the next line again. For example, on the third line, we are now sure that the element is not null, but maybe it's a PSI variable. If it is, then we use variable validate, and if it is valid, we return it. On the next line, we are sure now that the element is not null, and it's also not a variable, but maybe it's a literal. Only when all our options are exhausted and we know for sure that the element is invalid do we return null from the when expression. Then collectFirst moves to the next element. This version of findFirstValidElement is a bit more verbose than the previous one, but I think we can agree it's much more readable. Even if you are tired and this is the last thing you do before going home, it's still easier to spot and fix problems when the code is written like this, with every step of the logic neatly laid out on a separate line and the mapping and finding abstracted away. There's one more approach to this issue that I'd like to show you. A lazy collection. or a sequence as it's called in Kotlin. It's a collection that evaluates its elements only when we request their values. For example, let's say we have a list of integers from 1 to 14 and we want to square them and print out the results, but only those that are less than 42. As you can see, at the end we only printed out the squares of the first 6 elements. However, just like in the naive implementation of find first valid element, we've already computed all the squares and only then realized that many of those computations were unnecessary. But if we use a lazy collection instead, which in Kotlin can be done simply by calling the asSequence method on our list of numbers, the results will be different. Now you can see in the terminal that the mapping was done only for the first 7 numbers, 6 that fulfill our predicate and the first one that does not. That's because the map method here is overloaded in the sequence class. Its lazy version does not create a new list with the results of those computations. Instead, it creates a list of anonymous functions, or lambdas, where each lambda holds the logic for squaring the original number. That logic is called only when necessary, not before. When we call takeWhile here with the predicate it less than 42, that it is not yet computed. The logic of the lambda is run only now, and the result of that operation is compared to 42. So we do this for the first lambda in the sequence, get the result 1, see that 1 is less than 42, take it and move to the next lambda. We run its logic, get the result 4, compare it, and so on. Eventually, we reach the 7th lambda in the sequence, run the logic, and get the result 49. The predicate fails, and that's it. We don't need to square any more numbers. Let's go back to our original example and try to implement a new version of find first valid element using a lazy connection. Here's how it will work. We have a list of code snippets. We turn that list into a sequence. Then we map each snippet to a lambda. The logic for that lambda will call the convert function, so we'll get a PSI element out of a code snippet. Finally, we call the first or null method on it, which will return the first element that passes validation, or null if no element successfully passes the validation. We can explain how the process works by moving backwards. We start with the first or null method, which wants to call the validate function and needs a PSI element for that. So it runs the logic under the it here. That logic, in turn, we move one line up now to read it, calls the convert function on the original code snippet. If it all works and the validate function returns true, we stop. We don't need to call either convert or validate on any more elements in the entire list of code snippets. Only if validate returns false do we move to the next element, that is, the next lambda. Great, it works. No unnecessary conversions or validations. And if we were to write a more complicated case, where for example convert can fail, we just need to make it return null and ensure the logic inside the lambda recognizes that if it receives null, it's always a failed validation. This way we don't have to call validate at all.
You may ask, why not use lazy collections all the time if they are so great? Well, there are some limitations. First, creating a lazy collection and accessing its elements will always be slower than in the case of a standard collection. So, if you predict that you will traverse your collection from beginning to the end with no early return, then actually making it a lazy collection may hurt your performance. Second, Kotlin's implementation of sequence is designed specifically for situations when to compute element at a given index requires us to know the values of elements at all the preceding places. So if you want to access, let's say, element at the index 3, then to do that, sequence will compute elements at 0, 1, 2, and then 3. What's more, the result of the computation will not be memorized. That means that if at some later point you will want to access that element again, Kotlin will compute that element again and also the preceding elements. This is because Kotlin has to take account of the fact that in the meantime, some of the data that we accessed for computation may have changed. It may also mean that our own code, the one we trigger, has some side effects. For example, we may leave a logline somewhere in the journal. The implementation of sequence must cover for such cases. So yes, for many applications, lazy collections will not be a good solution. Sometimes instead you may use an early return, and sometimes you may use something like what I presented before, with collect first and when guards. But sometimes a lazy collection is exactly what you are looking for. In those cases, we can write code that looks exactly like the naive version we talked about before, and then add something as simple as dot as sequence. You may often hear arguments that languages like C, C++, low-level languages, are faster than high-level languages like Java, Kotlin, and Scala. And as a form of evidence for that claim, you can look at benchmarks where algorithms written in different programming languages are being compared. In such cases, yes, the same algorithm written and executed in a low programming language will be faster. But this is not how real world works. In the real world, we don't have exact same implementations of the same algorithm written in different languages, and we don't just compare them. Instead, we have lists of requirements and we have deadlines. And we need to write code that will fulfill that list of requirements before the deadline. And if we do it in a low-level language, it means that probably we will spend much of that time writing some simple version, and there will be little time left for optimization. Instead, in a high-level language like Kotlin, we can first of all spend less time working on that first simple version of the algorithm, and then we have more time to tinker and to add an optimization or two. And some of those optimizations can be as simple as adding one line dot as sequence and improve the performance just like that. And that's all. Thanks for watching. To learn more what IntelliJ IDEA can do for you, look for more videos on our channel, read our blog, and like and subscribe. Happy developing!